Yeah, thanks for the invitation to talk today. So I represent our group, that's the NIAC Phase 2 group. Thanks, Jay, very much for that. It includes the University of Arizona, Southwest Research Institute, the Applied Physics Labs, Jet Propulsion Laboratory, ASU, and Cornell. Just like any new big project, it takes a whole village to make it happen. And again, I'm Chris Walker. I'm at the University of Arizona. Next slide, please. So why are we all here and why do we all care? We live in a galaxy comprised of stars, planets, and people. We want to know, where does it all come from? That's the big deal. When we wake up in the morning, we want to understand where we are, what we're doing, and where we're going. So we work on the how did we got here part. Next slide. And we do have an idea. Where we come from is the interstellar medium, the ISM. That's the gas and dust in between the stars. This picture was taken from Mount Graham, Arizona, on a perfectly clear night. So everything you see up there is real, that's hanging in the heavens. And if you lived 100 years ago, you would get used to seeing that picture. You know, the first time I ever saw that was, I was like 25 already before I got to a clear sky. This is where we come from. Every atom and molecule within our bodies comes from this interstellar medium. So we have a strong primeval connection to it and trying to understand it. Next slide. And it turns out that many of these atoms and molecules in the ISM, from which we all came about 5 billion years ago, have important transitions, atomic and molecular transition at far infrared wavelengths or terahertz frequencies. And terahertz frequencies are frequencies about 100 or 1,000 times higher than the typical cell phone frequency. And one of those lines, emission lines, is water, atomic water, 557 gigahertz, molecular water line of 557 gigahertz has a ground state transition. And this, of course, is very important for understanding the origin of life. And water has been detected in space, most recently by the Herschel Space Observatory, which is a joint mission between NASA and ESA, European Space Agency. And here's some example of what these water lines look like. These are from an evolved star, but they also have been seen toward protoplanetary system, perhaps tracing primordial Kuiper belt objects or Oort clouds, as is shown in this picture here. And so the trouble with terahertz frequencies, where all these nice lines, emission and absorption lines lie, is that it's at terahertz frequencies. And the trouble is that the Earth's atmosphere, the water vapor in particular, absorbs almost every photon of terahertz radiation before it hits the ground. So we have to get up high to get away from the atmosphere. Next slide. Here's a NASA provided slide from a program manager a few years ago, which shows the NASA portfolio of flights as a function of frequency. Here's a wavelength. Here's radio, microwave, infrared, on up we go into the X-rays and gamma rays. And the terahertz regime, the one I'm talking about that really traces the ISM really well, the interstellar medium, is right here. And the only things we got going, we have SOFIA, which is a 2.5 meter aperture telescope limited in size by the fuselage diameter of a 747. And then we have JWST, which will fly later on. And as someone mentioned earlier, JWST is great, but it has a dedicated suite of instruments, none of which are suited for probing these terahertz emission lines at high spectral and spatial resolution. And there's SOFIA, and we're limited to 2.5 meters with SOFIA. And also SOFIA can only fly so many flights a year, and there's only so many hours available. And it's very highly competitive. Next slide. So what are we going to do? What's next? Because there's not going to be any more big space missions in the next decade or so, other than the ones you see here. So what we can do next is we can use ballooning. Ballooning is a great way of probing the terahertz regime at a relatively low cost. And Seth and Ben showed a nice slide of a balloon gondola earlier this afternoon. Next slide. So the concept we have is this thing called the large balloon reflector. And normally, like for the gondola that Seth and Ben showed, the gondola lives down here. This is what a typical long-duration balloon flight train looks like. You have this, what we call the carrier balloon up here. It can be 100 meters in diameter. You have a parachute with explosive bolts, or they may be thermal, I don't know. Vernon would know, he's in the audience. And so basically once you go around and you're done, you can release the parachute and this thing opens up and it floats back down like an old Mercury or Gemini capsule, and you can pick it back up again. We actually have an ongoing program called the Stratospheric Terahertz Observatory, and we have a 1-meter telescope that's down here making observations at terahertz frequencies. But the size of the mirror is limited not so much by weight, but by the ability to point. What we'd really like to have is a 10-meter telescope, something that can collect a lot of those precious photons from space and provide sensitivity and also angular resolution, which scales with the diameter of the telescope. So the idea we had, which we put forth to NIAC, and luckily they thought it was okay, was why not put a balloon within a balloon up here and make a 10-meter reflector? As we heard in Kimberly Smith's talk earlier today, a natural shape for a big mirror is a sphere, and it's like one of the oldest mirrors people have used as spherical mirrors. So I said, hey, a natural shape for a balloon is a sphere, so why don't we blow a spherical balloon up inside this larger balloon, which kind of you think of acts like a radome, and then metalize one part of that balloon, and then use it as a spherical reflector or a spherical mirror. Next slide. So here's a kind of schematic of what it looks like. The terahertz light comes in and it passes through the outer skin of this carrier balloon, which is basically kind of like the plastic from dry cleaning. It's really pretty transparent. In fact, I'm not sure in this presentation I have it, but we have an FTS spectrum of this balloon material, and it's more than 95% transmission at terahertz frequencies. It's basically just not there. In fact, this same kind of balloon material you can use as a beam splitter, and like a lot of terahertz guys like me use beam splitters in their instruments. So anyway, it's 95% or better transmissive, so the light comes through here. We'll just move over here to this inset here. Comes through the outer balloon, the near side of this inner balloon, which forms this 20 meters in diameter, bounces off of a metallized surface in the back, and comes to a focal line. That's the issue with spherical mirrors. They don't have nice focal points, they have focal lines that you have to correct for, like Kimberly was describing earlier today. Next slide. And so if you go inside this balloon, you can see one way we help maintain the shape is there's actually dielectric curtains, they're called, which are strung across it that are orthogonal to the incoming wavefront. So you blow up the balloon inside and it pushes out against these, like this skeleton of dielectric inside that helps maintain a spherical shape. And also these dielectric curtains are orthogonal to the incoming wavefront, so they provide minimum, essentially zero absorption or diffraction effects. Next slide. Now, is this totally crazy? Well, no, I don't think it's totally crazy. It's crazy enough for a NIAC, thank goodness, but it's not totally crazy. And that this has been around for a long time, this basic idea. Here is ECHO 1 satellite, 30.5 meter diameter sphere, luminized mylar, circa 1960. And I actually am old enough to remember this. My dad pointed it out to me one night after a PTA meeting when I was a little kid, saying there's ECHO up in the sunset. And this actually wasn't a stratospheric reflector. It actually was inflated in orbit. So everything I'm saying about this in a balloon for stratospheric work, you could also do it in orbit because it's been done before. This actually was done first in orbit. This was a passive reflector. The whole thing was illuminized. So you'd bounce a strong signal from the ground off of it and back again. I think Eisenhower had the first communication through a satellite like this. Next slide. Okay, now the idea of using inflatable telescopes is not new. It's been tried and it works to some extent. This is a picture of a parabolic inflatable reflector from an earlier STS-77 mission. It had a 14-meter parabola. Parabolas are great. This is what you want because the parabola has a single focal point, which is what you want to put your nice MKID detectors or transition edge detectors at. But the trouble is it's difficult to maintain the surface figure of a parabola to high accuracy. So if you go beyond 10 gigahertz X-band, maybe you want to go 557 gigahertz where this water line's at, or maybe 2 terahertz. You can't hold the parabolic shape very easily. A sphere is a more natural thing to use. Next slide. Okay, so we have to have a spherical corrector. Now these are not new. Kimberly pointed out some work by Roger Angel and Jim Burge, but it's been around a long time. Here is the Arecibo radio telescope, which is a spherical reflector. It's about 1,000 feet across, 305 meters. And at the focus, it used just to have these line feeds. You might remember some of you guys remember those. You get a focal line, you have all these little feeds and have a waveguide, and they add up in phase to go to your detector. But not so long ago, Frank Drake, Paul Goldsmith, and others decided, well, let's have a reflective spherical corrector. So basically, the light comes in from the spherical reflector here, goes through this, creates this focal line, re-expands. You have this crazy-shaped secondary mirror, which brings it to an intermediate focus. This is an off-axis Gregorian design. And then after bouncing through these two surfaces, it will come to a single focus where you have your receiver. And this has been in operation for some time. I've walked around inside of this thing. This is like 80 feet across inside. So what we're doing with LBR basically is we're scaling a 305-meter Arecibo down to 10 meters and trying to make it work at a higher frequency. Next slide. Okay, so in NIAC Phase 1, we were able actually to build a test of this. And this basic idea of using a spherical reflector and using it at high frequencies. So what we did was we bought a $350 walking sphere from a toy company in China, which is designed for kids to get inside and hopefully not suffocate and walk on water and stuff like that. So we got a supersized version that was 3 meters in diameter, and then metallized the back of the surface. And this is the only thing the students would let me do, was to spray paint on the outside of the sphere. And then we had the receiver system inside. This is Abe Young. He's actually 6'3", and he's inside this balloon with the Schottky receiver system. And what happens is we point it over at this reflector. Next slide. Okay, great. And this is it assembled with the students who made it all happen. You're looking from the outside, this tuning fork structure with the receiver looking at the reflector is inside the balloon. It's inflated just like a jumping castle at your kid's birthday party. Next slide. And we tested it not at 557 gigahertz, but at 115 gigahertz. We had a lot of stuff laying around the lab from that. We had 115 gigahertz test transmitter. Here's what would be LBR. Now, in the actual flight version of this, remember, this is the inner sphere. The outer carrier balloon is like this, would be over it. Next slide. And then we actually were able to we had a spectral line receiver in it. We could see test tones, just like we would observe a water line. And then we did a scan of the sun, and sure enough, even on a kind of messy day in Tucson, we were able to see the sun at 115 gigahertz and get diffraction-limited performance, even with this very low-tech, crude system, which makes me think maybe in reality we can make this thing work. Next slide. Now, we're in NIAC Phase 2 now, so what we're doing is we're making a 5 meters diameter sphere for two reasons, 5. One is that we can afford to do it at 5 meters, get an actual balloon made, and it also fits within the available high bay hangar at the Southwest Research Institute where it exists. So basically we have a 5 meter version of this. We haven't installed them yet, but the idea is to have these internal curtains to help support the structure and make it to a sphere with differential pressure and stuff like that. It hangs from a overhead crane so we can test it. Next slide. Here's a picture of it. It's undergoing tests now at the Southwest Research Institute. This is actually a video. Maybe go ahead. Could you start that video? It moves rather slowly. We'll see. Yeah, okay. There you can see it turning. It's turning in azimuth now. And if you look up here, you can see how it moves in elevation. But it's all going very slowly. I don't want to bother you with that, but it's kind of cool to watch it move up and down. How about let's stop that and go to the next slide, please. All right, now what about that crazy spherical corrector? Well, this is actually the design that's from Arecibo that's simply scaled to what we need for LBR. And here's some dimensions on it. And so we've actually have created, the first thing we did was make a 3D laser printer version of this. Next slide. And that's what it looks like. All assembled. And it's actually, you say, well, how big is it going to be? Well, for a 20-meter diameter sphere, which gives us a 10-meter aperture, this whole corrector unit is about 1 meter in diameter, the whole thing. is all it is. And you can actually build it so it's integrated and sort of self-aligned. But still, there's issues, right? Because you wonder, well, how spherical will that inner balloon really be? Is it going to have gravitational sag? Is something going to, maybe the balloon doesn't, from the manufacturer, some of the gores, which like the gores in a pumpkin, form it are out of whack and it's not perfectly secure. How are you going to deal with that? So what we need to look into, and we have been looking into, is making this, this secondary mirror here adaptive. Next slide. Okay. And here's the Mark I version. We have a Mark II version we'll show Jay later in the week. But here's a Mark I version of this mirror. Can we go to the next slide and start the video for that? Okay, and so here it is in the lab in Tucson. This was built by a grad student in 3 days. That's how he works. He doesn't sleep for 3 days. Then you don't see him for 3 days. But anyway, it works. And so you can see how flexible it is for compensating for non-spherical distortions in the balloon. And the thing that makes this very important is that it's hard to get a piece of rubber to be reflective. And so the idea we had as part of NIAC Phase 1 is actually got a bottle of silicone liquid from Home Depot, and we got some aluminum powder with sub-millimeter size grains in it. And basically you load up the silicon sort of half and half by weight, and then it's 80% reflective at 115 gigahertz where we were testing it. And you can just flex the heck out of it. So you can make it do whatever. You can make the crazy shape. In principle, we haven't done it yet, but you can almost certainly be able to compensate for large-scale, slow, non-spherical distortions in the balloon itself. Thanks. Next slide. All right. So to correct for those non-spherical distortions, you have to know what they are. So another important factor we had to work on in Phase 1, we're working on Phase 2, is metrology. How do you do a metrology of the balloon? Measure the surface in flight. And we had a couple of ideas. The obvious one was to get a laser ranging system like from Faro, which we got one on loan. This was at Southwest Research Institute. That's Steve Smith, who helped come up with this idea with me. And he did some measurements, and yes, you can measure the surface, but then the laser scanner it spins around in azimuth and elevation. It kind of makes you worry how well it would work in a balloon at 130,000 feet. So the grad students, next slide, actually had a better idea. I don't know where they got it from. They know about this Kinex. Kinex is this thing on your Xbox 360. And so one of the grad students, Brandon Smith, who's shown in a silhouette right there, said, hey, why don't we use the Xbox? I said, what are you talking about? He says, well, how an Xbox works, which I had no idea, was it has an infrared laser, and it runs it through a grating. The grating splits that laser up into hundreds of little infrared dots, which paints your kids and your whole den in these dots. And the Kinex knows what the separation between those dots is in the real universe when it leaves the emitter here. And so what it does then is it uses an infrared camera to see where those dots fall. And it does just a simple parallax calculation. And of course, the further away the object is the dots lie on, the farther the separation, the dots will be on the infrared camera. So it can work back and get a 3D picture of your family room that way. And it does it to about 1 millimeter accuracy. So we actually take the one from my kid at home, we took it in, Brandon put it in the balloon, and we were able to measure the inside surface to about 1 millimeter just using, Xbox 360 unit from GameStop. Next slide. But the trouble, I'm sorry, can we back up one more? I got ahead of myself. The trouble with this Xbox type approach is that it's in the infrared. And it worked great on our rooftop prototype until the sun came up. And then you overload the infrared detector. So the simple solution is, hey, when we get the balloon material made, we just have dots printed on them at a specific separation. And then we make it so they're painted either white or black, not sure which yet. And then we can just use regular webcams, basically, a series of webcams to look at the surface and measure the dots and their separation. And we have a system working in the lab, which we'll hopefully demo for Jay later in this week. Next slide. Okay. Now, you have to have power, you have to have pointing control and things like that. So what you have basically, even with the LBR on the top, you do still have a gondola hanging from the bottom called a service gondola. Service gondola provides power, communications, and also holds some computers and all that kind of stuff. And so in our case, the surface gondola looks a lot like this is our STO gondola, which will fly again later this year from Williefield in Antarctica. So the gondola and many of the subsystems are made by the Applied Physics Laboratory. So the gondola and the pointing system for LBR is basically a straight carryover of technology that was developed for STO. Next slide. All right, so how would this thing actually work? Well, here's what a LBR test flight profile would be like. And what we're hoping to do next is to convince folks at NASA that we would like to do a test flight of this technology after phase 2. So this is how it would go for a test flight, say, from Fort Sumner. Well, his pictures are from Antarctica, which we hope to do too, but not until after you do the Fort Sumner one. So basically what happens is when you inflate these balloons, they lay them out on the ground, and they have these tractor trailers full of helium that inflates it. So what you do is that on the top of the balloon, you have a plate, much like the Top Hat experiment did back in the 90s, where they had the telescope on top of the balloon. So there's a plate here, and in that plate there's an aperture, and you basically slide in an LBR canister. It's something about, about the size of a coffin, 2 meters tall, maybe a meter in diameter, that contains the actual de-inflated, packed LBR sphere with the instrument module inside with a receiver system in it. You slide it in right there on the flight line, and then it's held up while you inflate the back of the balloon with a tow balloon. This is just exactly what they did on this Top Hat experiment about a decade ago. And then that holds the weight of the LBR canister, which you see in yellow right there. Maybe you can see it, until the bottom balloon is fully inflated. And then once it's fully inflated on the ground, this tow balloon is released. The balloon goes up. As it goes up, the air pressure goes down, some collars are popped here, and the outer carrier balloon is allowed to expand to a full 100 meters in diameter. And at that point, what you do is you basically use blowers, just like at the park with your kids, jumping castle, to take some of the helium, 17 million cubic feet of it, from the carrier balloon into the LBR balloon to inflate it. Okay, and that's done once you're near float altitude, which we want to go as high as we possibly can, 125, 130,000 feet, to get above as much of the water as we can. And then you float, you take data, you do water measurements, and then you come down. And normally with a balloon, you have, as I mentioned earlier, this one parachute that carries your payload down, but we'll have 2. We'll have another one that's launched with a mortar on top to help bring down the inner balloon, because on the LBR balloon itself has the receiver system in it, which I haven't had time to go into. You'd like to recover it if you could. And then it comes down, so you actually have 2 payloads, 2 parachutes coming down. Next slide. Okay, and so now we're in NIAC phase 2. We'd like to have the opportunity to propose for a test flight as early as 2018. After NIAC, that's where we'd like to go if the fates allow. And then next slide. So what's the cost benefit of this? So here's a little comparison between just the costs. JWST comes in at more than $5 billion. SOFIA is at more than $1 billion with a $70, $80 million a year operating budget for a 2.5 meter telescope with a warm aperture. Now LBR, with a 2-flight series, one from Fort Sumner, one from Antarctica, comes in at under $10 million, is what it would cost. So it doesn't do it doesn't do everything that these guys do. It doesn't do anything JWST does. It does some of the terahertz work that SOFIA does, but just comparing costs, it's like not there. It's about as transparent as the balloon material. Next slide. Okay, now what next for LBR? This is the last kind of fun slide. Well, recently we're thinking, working with our friends at SWIRI and JPL, maybe LBR has another role as well. Maybe not at the crazy terahertz frequencies where we're interested in, but maybe as a humble X-band reflector that can be used in environments such as Titan. There's a lot of interest in Titan missions. So here's a nice graphic from our friends at SWIRI. Talking with Ralph Lorenz about this concept from the Southwest region, from APL. What excited him most about LBR was the idea, he's an expert in Titan, I am not, was the idea of using it as a telecom dish for a high gain. And that's important because back when I was at double E school, I remembered that the bandwidth you can transmit back to Earth, or you have in a telecom link, is proportional to the power, radiated power. So for a given amount of transmitted power, you want the biggest dish you have. The bigger the dish, the more information you can coax back to Earth. And what limits the science is not the technology here, just simple infrared cameras floating a kilometer to a couple kilometers above the surface would bring back tremendous amounts of data. The trouble is currently there's only like a soda straw that you have to sip that data with. Whereas if you had a 10 meter, or well, I guess what Ralph suggested was a 5 meter diameter LBR, then you can actually get tremendous amount of data back to Earth, even with a fairly simple payload. Next slide, and I think this is the last one. So I hope I've imparted some of my enthusiasm for this project, and thank you for your attention, and I'd welcome any questions.
I have a question.
Sure.
So you partially reflect part of the sphere. I mean, you're breaking that. What prevents it from potentially inflating at a wrong angle in which you're not aligned and you won't see your primary?
Okay, well, the whole thing is actually is on an azimuth and elevation track. So you can rotate it in azimuth any way you want, and you can rotate it in elevation from 0 degrees to 70 degrees. So you can actually move it around to compensate for that.
Okay.
I presume if you're using an internal skeleton of dielectric sheets of some kind as a structure, wouldn't that provide you the ability to produce a parabolic shape on the inside of the whole balloon itself?
Yeah, in theory, yes, you could do that, and I'm sure it would work. I think it would work up to, based upon what work's been done, maybe up to maybe 50 gigahertz or so. It's just that you need to be, the figure needs to be held to lambda over 16, basically, for most of the photons to show up at the focus. And the wavelength, like that 557 waterline, it's about the same as the frequency in microns. It's like 550, 30 microns, something like that. So divide that by 16, it gets really scary to hold that parabolic shape to that level. So yeah, I think it could be done, but it's easiest, I think, and it'll more easily be made to work if we make it a sphere. The other thing I didn't mention is that a sphere actually can work as a parabola as long as you under-illuminate it enough. For instance, say you don't believe that we can do this spherical correction stuff, that we need to get a 10-meter aperture. The same 20-meter diameter balloon, if you throw away the spherical corrector and just under-illuminate it to about 2.5 meters, will work just fine as a parabola. You have to go out further along the sphere before it deviates from parabola enough to mess with you. So even without a spherical corrector, the spherical balloon will act as a parabola, a 20-meter diameter one to about 2.5 meters in diameter. Well, thank you. Appreciate it.